Hey, welcome back. Now, don't worry, I haven't gone crazy. I was just preparing for today's episode about the stack. So, today we're going to talk about the CPU stack and something called zero page. But let's start by talking about the stack. Let's start by looking at an example here in code. So I'm going to show you why we need the stack, or one of the reasons it's so nice to have the stack. So if we can imagine here now that I have some sort of code. Now we talked about subroutines last time. So now we have this subroutine here called drawChar. So it's going to draw a character. So we have a routine here with an RTS at the end. All right, cool. So now I just want to draw 100 characters for whatever reason. So here in my code, I wrote a little loop that says draw characters loop. I just want to draw a bunch of characters. So, alright, I make a little loop. I say load x with 0, like we often do when we're making loops. And here in my loop, I also increase x by 1, compare x with 100, because I want to run this loop 100 times. And it says branch if not equal draw characters loop. So I'm just going to go up here. This loop is going to run 100 times, right? But what's happening here in this loop? Well, for every time the loop runs through, we are running this subroutine. Jump to subroutine, draw character. All right, that makes sense, right? If we have a subroutine, it's going to draw a character for us. And we just want to do that 100 times. Sure, no big deal, right? Well, now we need to take a closer look at what's actually going on here. First of all, let's just confirm this. We use a loop by loading x with 0, and just to keep track of the loop, we use this method by increasing x, comparing x with 100, and if we haven't reached 100 yet, we go up here. So we keep track, by using the x register, we keep track of the loop, right? Just increase x one time for every time the loop runs through. But also here in the loop, every time the loop has an iteration, it also runs my subroutine, draw character. That's going to happen 100 times. So what's going on in draw character? Well, let's take a look at the subroutine down here. So the very first thing in my draw character, drawChar subroutine, is load x with tile row, it says here. So that's gonna be a very big problem for us. Now, don't worry too much about the logic. This is just an example, and I'm not even sure if it's going to run. But the point here is to show you that right now we have a problem. I'm using the x register to create a loop. And inside my loop, I run a subroutine here called drawChar. That subroutine also uses the x register, which is a problem for us because by the time already the first iteration of the loop, when we run this drawChar, already the first iteration, this becomes a problem. We're loading x with something else. So we're sort of corrupting the x register. We're loading another value into x, which is going to break our loop. We're no longer keeping track of the loop. So by just increasing x once for every iteration of the loop, that's broken now. Because the first time we ran this draw character, drawChar, the first time we did that, we already overwrote whatever was in the x register. So we're loading x with some kind of number here. We don't know what it is, it doesn't matter. But we're loading x with something else. So we're loading x with that, we're doing some stuff here to draw a character. RTS, return from subroutine, sure. And now we're back here. we say increase x. But what's in x right now? Well, down here we loaded x with some sort of tile row. We don't really know what that number is. So the problem here is maybe tile row was 20, whatever. So we loaded x with something else, which means that when we get to this point in the loop, so let's say it was number 20, okay, increase from 20 to 21. And maybe this loop was supposed to just run 20 times or whatever. So if we loaded x with, let's say this tile row was 19, right? Tile row 19. That's what happened in our draw character and we ran this. So by the time we get out of the draw character subroutine and we return back up here, now we have 19 loaded into x. So we get down here, increase x by 1. So now x is 20. Compare x with 20. Is it 20? Yeah. So we don't branch up here and we just continue on. So that means that this, in this case, this so-called loop we had just ran once. Now, it wasn't supposed to be that way, but because of this thing, we suddenly loaded x with something else, so we broke the logic of the loop. So here's where the stack comes in to save us. So we need to make sure that we make sort of a backup of whatever's in the x register in this case. So we are sure that by the time we get down here, the x is exactly the same as it was up here. So we can do that by, let's see here, we can do that by using the stack. Now we're gonna take a little closer look at what the stack is, but let me just show you right now. Now I'm going to say transfer x to A. Copy whatever's in x into the accumulator. Then I say PHA, push whatever's in the accumulator onto something called the stack. So copy whatever's in the accumulator right now to the stack. I'm gonna take a look at the stack in just a second. So basically what's going on here is that we're making a copy of whatever's in x in some sort of safe place called the stack, right? We are running the draw character routine, draw char, which loads something into x, does some calculations there, and when it's done, we get back here. So now we can say PLA, pull from the stack into the accumulator. So give me whatever the last number was, give me the number that was last put into the stack. I'm gonna pull that number from the stack, put it into the accumulator. Then I say transfer the accumulator to x. So copy what was in the accumulator into x. So put in simple terms, here we're making a backup of whatever's in x. We run this routine, which messes a little bit with the x. It doesn't really matter, because when that's done, we get to here and we get back that backup of our x. So for example, if x was 5 up here and we get it back here, it's still going to be 5. So the draw character loaded something in here, maybe it loaded 19, whatever, it doesn't matter. We made a backup of x up here and we recovered our backup here. So by using this stack thing, we can make sure that we don't mess up our code by loading different things into the registers. Yeah, we make sure that we keep the right value, for example in this case before and after running a subroutine. But right now let's take a closer look at the stack. At the very beginning of this video I was stacking some dinner plates, one on top of the other. Now that's a simple example to show you that we have something called first in, last out. So if I stack my dinner plates one on top of the other like that, then the last one I put on the stack is the first one that I take from the stack. So let's take a look at this. Let's try to combine that sort of symbol, the analogy, but with the stack of dinner plates. And let's see how that would work in the CPU stack. So we have an area in the Commodore 64 memory assigned to the stack. We also have a little thing called the stack pointer, which I've drawn a little hand pointing like that. That stack pointer points to, keeps track of where we are in the stack. So now my stack is empty. Now I'm going to add something to the stack. So let's imagine this dinner plate thing, right? I add a dinner plate. But in reality, it's not a dinner plate, of course. In reality, what we add to the stack is a byte. We add 1 byte to the stack. Then I add the stack pointer goes up. It keeps track of where we are in the stack. Then I add another dinner plate. Another byte. Stack pointer goes up, keeps track of where we are. I add another byte. I add another byte. Another byte. So we can add something to the stack 256 times. Well, somewhere around there, because the stack is 256 bytes. So we can add something to the stack like that. And we're doing that for every plate I put here into the stack now. Every byte. That was a push, PHA. You just saw I'm sorry. You just saw me use the mnemonic PHA, which means push to the stack. So in this case, that was pushing those dinner plates. So for every time I use that PHA, that's gonna push whatever's in the accumulator onto the stack. So we can only push what's in the accumulator. So that's why in the previous example, I first had to say TXA, transfer X to A. So first transfer X to A, so that whatever was in X is now in A. Then we can run PHA, push whatever's in A right now onto the stack. So right now I've run the PHA mnemonic 5 times. We have 5 dinner plates here, or 5 bytes. So what happens if we need to remove something from the stack? Well, we pull from the stack. PLA, pull from the stack. So we pull from the stack into the accumulator. When you write the mnemonic PLA, you get whatever was on top. Let's imagine this thing. Get the top plate, right? So the last thing that was put into the stack, that's what you're getting. And you're getting that into the accumulator. PLA, pull from the stack into the accumulator. So now I'm going to use PLA again, and I pull that from the stack, and that byte goes into the accumulator. and my stack pointer keeps track of where we are in the stack. We don't need to worry too much about the stack pointer because the computer keeps track of that for us. But point is, PLA, I grab what's on top of the stack, what was added last, give me that, PLA, give me the next thing, PLA, give me the next thing. So by doing that, we can use this like we just saw as some sort of, I don't know if we can call it backup system, but a system to make sure that I have a value here. It's very important. I'm going to need that in just a little while, but first I need to do some calculations in the meantime. So this could be the X register, could be the Y register, or it could be the accumulator itself. So we just need to make sure that we as programmers know that we need to keep track of this number, the number that's in, for example, in X right now. I'm going to need that number in just a moment, but first I need to use the X for something else. For example, like a loop that we just saw. So hopefully that makes sense. The stack is there to help us do these sort of things. Now it's also very important to remember that we need to do this in the correct order. So when you push something to the stack, you need to pull it from the stack. So I could do several things here. I could say, oh wait, I need to keep track of both my X register and my Y register, for example. So here I say transfer X to A, push to the accumulator. No, I'm sorry, push to the stack. Transfer X to A, push that to the stack. Down here I say pull from the stack and transfer what's in A now to X. Now if I also need to keep track of my Y register, I don't want my Y register to be corrupted. Maybe for whatever reason, maybe have some more loops here, something like that, whatever. So I could say, alright, transfer X to A, push A to the accumulator. Now the X value is safe. Then I need to say transfer Y to A. So we copy what's in the Y register into the accumulator. Alright, then we say again, push what's in the accumulator right now to the stack. So first we said transfer what's in X into the accumulator, then push that to the stack. Then we say transfer what's in Y into the accumulator, and then push that to the stack. And remember these dinner plates. For every time we use PHA, we stack another plate on top of our stack. Alright, so then we just run our whole thing, no problem. Don't have to worry. Maybe Y was 98, whatever. And then we run this thing. But now we need to be careful. We just pushed two things onto the stack. One thing, one dinner plate, two dinner plates. So right now we have two values in the stack. We need to retrieve them in the correct order. The last thing that I put into the stack was the value for Y. You remember here. Transfer Y to A, push that to the stack. So that's the first thing I need to get from the stack. So here I need to say PLA, pull from the stack into the accumulator. Pull from the stack into the accumulator, then transfer A to Y. Transfer what's in the accumulator right now into the Y register. Transfer A to Y. And now I have 98 in Y again. Then I can say pull from the stack again into the accumulator. Now I want you to transfer A to X. So transfer what's in A right now into the X register. So now I have 5 in my X register. So it's just a very convenient way, not just convenient, but sometimes this is essential. We need to do this. Because if we don't do these sort of things, and we run some sort of thing here, for example in this case, something that's loading something into X, and this draw char even loaded something into Y. So I would have to use this trick anyway. I would need to keep track of both X and Y anyway, because my draw char subroutine loaded something both into the X register and the Y register. Load X, load Y. So in this case, this was a really good thing. Make sure that we keep track of X register and the Y register. So we need those values to be the same up here and down here. So hopefully this makes sense. So the stack is there to help us with things like this. And let's just quickly also take a look at something. The stack is located at address 100 in the Commodore 64 memory. It goes from 100 to 100 FF. So 256 bytes is set aside for the stack from address 100. Now, I think we should be a little bit careful to go too much into detail here. Maybe that's enough. But we should mention something here. So just as some sort of best practice, this is something that I just recommend that you do just to be safe. Your program, your game might run fine without it, but this is just some best practice, just to be absolutely sure. So what I'm talking about is initializing the stack. What we often do is say LDX with the number, hexadecimal number FF. So I'm going to load FF. FF, that's 255, right? I'm going to load X with 255, or FF as we see here. Then I'm going to say transfer what's in X to the stack. Load X with FF hexadecimal, TXS, transfer X to the stack. This will initialize the stack. So here's the weird thing. Let me just get this out of the way. So the stack is sort of upside down. Let's take a look at what I mean. So if we take a look at the stack now, excuse me, we see that this bottom value, that's 100 FF. The next one is 100 FE. Next one 100 FD, and so on. So it goes down like that. You would think that it would go the other way. So 0, 1, 2, 3, 4, 5, and so on. But it's actually the opposite. So the start value of the stack is 100 FF, which is why we did that thing by initializing the stack. Initializing a stack is, as I said, it's just a best practice, and I recommend that's something you do for very first thing you do in your program. So your program might work without it, probably will work okay, but just to be sure, just one more thing that we can check off as okay. So load X with the hexadecimal number FF, right? Transfer X to the stack. Just these two things to initialize the stack. It's a good idea to do that. All right, well, hopefully this stack thing makes sense to you now. And now we can start talking about zero page. So once again, let's start by looking at the Commodore 64 memory. So we just looked at the stack, which starts at address 100 to 100FF. That's the stack area in the memory. So here, almost at the beginning. Now we have something called zero page. That's also an area in the Commodore 64 memory, but that area is at the very beginning. So the very first 256 bytes in the memory. So if we take a look at this, we can see that zero page goes from 0000, very first address in the Commodore 64 memory, and it goes all the way up to 00FF. So from 00 to 0000 from 00FF, first 256 bytes. That's what we call the zero page. So a page in the memory, that's 256 bytes. And the very first one is called zero page. Now, right off the bat, you might not think that that's something special. It's just a part of the memory, right? And that's sort of correct. It is part of the memory, yes. But we can use it for something special. We're going to take a look at that now. So you remember this loop, right? The loop for writing all the characters in the character set to the screen, the Commodore 64 screen. So let's run that now just as a reminder. So here we go. So what this little loop of mine did was write every character in the character set to the Commodore 64 memory, starting from the very top, writing all the way like that, 256 times, right? So that's what my little loop did. And as you remember, 0400, that's the address for the top left corner here. So that's okay, right? Now, what if I wanted to continue writing something here? Now, that's going to be a little problem by using this little loop, because this little loop uses the X register as an offset. So at the very top here, the X was 0. So when I said STA 0400, X, the first time the X was 0, so that was just address 0400. But remember this X thing, this offset, we add what's in X to this address. So when we say increment X, X goes up by 1, and we get up here to a loop again. So the next address will be stored at 0401, because now the X is 1. So that's this next one. But we know that 8-bit computers, like the Commodore 64, can only hold numbers from 0 to 255. Which means that the last one here, so the largest number in X will be 255. You can never have a number larger than 255 in any of our registers. The X register is no different, of course. So it just stops here, right? It just stops there. So how could we go about placing a character anywhere we want on the screen? Well, this loop thing is not going to help us to do that. But what if we could make our own memory address, so to speak? What if we could manipulate this address so that I could place a character down here if I wanted, or maybe here, or up here, or wherever I want? What if I also could make a system that says I want to place a character that's 12 rows down and maybe 20 rows from the left to the right. So some sort of logical system like that. Well, that's exactly what we need to do. We need to be able to place characters wherever we want on the screen, because that's how we're going to make our background graphics. That's how we're going to draw our tiles. So this thing is not going to help us. So we need to be able to make our own memory address. Well, not make our own memory address, but we need to construct a specific memory address. But how is that going to work? Let's take a look. So now we're going to look at something which is super confusing, and it's almost like I don't want to tell you what these things are called, because it's super confusing. Let's be honest. We're going to be using something called indirect indexed addressing. And let's not confuse that with indexed indirect addressing. Indexed indirect addressing, indirect index addressing. Yeah, let's just we don't need to use all these terms because it gets super confusing, right? The point here is that what we are going to do is that we are going to construct, like I said, we're going to manipulate some memory addresses, put them together to make a specific address. So instead of just using, like we saw before, a loop starting at 0400, we need some system where we can place our characters where we want on the screen. So the way we do that is by using 2 bytes in the 0-page memory. So first of all, let's take a look at something. So if we take a look at our memory address 400 here. Now these memory addresses, I don't know if you have thought about this before, but they are 16-bit. So a number like 1F, for example, that's an 8-bit number. This is a number we can put into the accumulator, or we can put it into a memory address. No problem. 8-bit number. Now this is a 16-bit number. So what we can do with this one, we can split it in 2. Now if we do that, we call this part the low byte of this number. This would be the low byte. This would be the high byte. So numbers like this, memory addresses can be split into low byte and high byte. So we are going to use that method to, as I said, sort of construct a specific memory address. And 0-page is going to help us do that. Now there's another source of confusion here, because there are so many things to keep track of now. We have briefly seen this before. Do you remember something called little endian? I briefly mentioned it a while back. Now the little endian, that's how memory addresses like this are stored in memory. So if we take a look at this, so here I could say STA, for example. I don't know why these are so small, but right. So I could say STA. Let's say this is my assembly code. I write something, LDA, whatever, and I say STA 0400. That's how my assembly code would look. Now in the memory, when we run this through the assembler and this is put into the memory, this STA, the mnemonic, is turned into an opcode. I'm sorry, I don't remember the opcode right now, but it's a number of some kind. But the important part here is, how is this memory address stored? So first we have the number for, oh no, XXX, probably not the best way. Opcode. So the opcode for STA is put into the memory of the Commodore 64. Then 00. That's going to be the next memory address. This is how it's stored into memory. Then 04. So this is the assembly code. You don't have to worry too much about this in the assembly code. We just write STA and the memory address that we want to use. But then we run the code through the assembler, and STA is turned into whatever the opcode was for that number. So that's the opcode, and that's put into one memory address. But then this thing is first of all split into two, and then this low byte comes first in the next memory address. Then the high byte comes in the memory address after that. So, like I said, these sort of things can be confusing. We have so many things to keep track of, and then suddenly we have this reverse thing, which just feels crazy, right? But it's there, we need to just deal with it. So, why is this important? This low byte, high byte thing. Well, this is important because now we're going to use low byte, high byte, that sort of thing in 0 page. And we need to use this in the absolutely correct way, because we are going to construct this memory address that I was talking about. So the way we do that, the way we construct memory addresses like that, is by storing, like we could see here, the low byte first and the high byte second. So let's look at this code example here. So first of all, what I did here in my code, I just made two labels. CP, that stands for 0 page. I said 0 page row, low. So low stands for low byte. And I just say that's going to be a label for me, and that label is address 0020. I make a new label called CP row high. That's going to be memory address 0021. So the very next address after this one. So the low byte first, and the high byte right after that. Alright, so those are just labels, right? And then we have this thing again, the clear the screen. Let's not worry about that right now. Then I say, down here, load A with 00. Alright, load A with 00, that's no problem. Store A into CP row low, which was the address 0020. So now I'm storing 00 into 20. The memory address 20. I'm storing 00 in there right now. Then I say load A with 04. Store that in CP row high, which is memory address 21. So the very next one after this, right? So maybe you recognize these numbers. We have memory address 0400. That's the top left of the screen, right? So basically I'm splitting up that memory address, but I'm storing the low byte first into 20. Then I'm storing the high byte in the very next address. So now I have that memory address stored into memory into 2 bytes. But like I said, low byte first, high byte second. Alright, then I say down here. And by the way, let's just visually see this. So this is the memory starting at 0, 0. So if we go all the way up here, you see what I have done right now. I've stored 0, 0 into memory address 20. I have stored 0, 4 into memory address 21. So now it's stored like this in memory. Alright. So what do I do next? Well, I load Y with 255 in this case. Alright. Then I say load A with 1. So in this case, that's going to mean screen code for the letter A. Alright. Now, here comes the magic. Look at what I'm doing right here. Now I say STA, store A into, in parentheses, CP row low. In parentheses, CP row low. This thing, comma Y. What's happening here is that now we are combining these 2 memory addresses. We are combining them into the address 400. Now, as I said, it's confusing because they are switched around like that, but that's the little endian system, and we just need to deal with it. It's there, we need to deal with it. That's just how it's done. So we have now the A, the number 1 that I'm loading in here. I'm storing that into memory address 0400. CP row low. So I use the low byte here in parentheses. I use the low byte in parentheses, comma Y. Now, by the way, this method only works with the Y register. We can't use the X register for this technique. But I'm basically loading into 0400. But another thing, this is not just address 0400. This is address 0400. But now the Y is an offset for me. So it's address 0400 plus 255. Now 255, that's FF in hexadecimal, which means now I'm storing it into address, let's see here, 04FF. That's where I'm storing screen code 1 right now. So I combined what was in these 2 memory addresses, 0400, combined those 2, and you know that's a reverse thing. So combining those 2 by using this parentheses, comma Y, so this offset. And this could be whatever. I can just specify whatever number I want in here. Actually, I could just write FF here, so I'm not confused here. So now I'm actually constructing this memory address. So now I can place my character further than you remember this loop we had, right? We could just go to 255. Now I've gone to the same address, because this was 255. So start at 0400 and we go to 255. Then let's see here. Yeah. So now I say increment Y. So move increase Y by 1. Now if I just said here, let's see, 0 0, so if y was 0, then we would just end up with address 0400, because y is an offset here, but if it's 0 anyway, and we just constructed 0400 here, then just y would just be 0, so 0 plus 0400 is 0400. So if I then say I and y, increase y by 1, it means move one column to the right, because this y is an offset. So in this case, LDA with 2, which would be the screen code for B. When I store this now, it would be at address 0401, because I just increased y by 1 here. And I'm still using y here. This is the same technique. So this probably takes a bit of practice to get used to. But this is a way that we can use to construct the addresses we want. So because we can use two addresses like this, we can construct any memory address as long as we remember low byte first, high byte second. Now I just used 20 and 21 for this. Memory address 20, memory address 21. It doesn't really matter too much. As long as we're in 0 page, this method will work, but it only works with 0 page. So, and also it's important that these addresses are right next to each other. So low byte and high byte in the very next memory address. So low byte and high byte. Yeah. So what happens now if I run this code? So now we can see that this first one, I'm just loading a screen for just loading 1 here, the screen code for A. And I just said, now I've already set up my low and high byte in memory here, because I loaded 00 into 20, I loaded 04 into 21. I loaded y with 0. So by the time I get down here, I've constructed the memory address 0400, and since the y was 0, the offset is going to be 0. So basically we end up with 0400, which turns out it worked fine, because here's the A at the top left corner. Then here I say I and y, increase y with 1, so go from 0 to 1, which in practice means I'm moving one column to the right. Then I say load A with 2, which is a screen code for B, and I'm storing that into the same thing here, but since y went up by 1 here, I end up at address 0401, so I get a B here. This is address 0401. So yeah, here I just play around with the y. So here I say load y with 255, load A with C, and try to store A in this address now. So you see we're still storing it in CP row low in parentheses comma y. So this thing looks the same, but because the y is different now, the y value offset, now this thing is stored down here. 0 all the way up to 255. So because the Y was 255 here, we got an offset for 255, which gives us this position. 0400 plus 255, or FF in hexadecimal. So that's how that system works. But how can we go further? That was the initial point with my character loop. I couldn't go further than 255. That was the problem. Well, now since we have full control over what memory address, we can make whatever memory address we want in here, right? What I can do right now, I can say increment whatever is in CP row high. Now CP row high, that's memory address 21. So memory address 21, that's this high byte 04. Now I'm increasing that, which means by increasing the high byte like that, we actually go up with 255. This might be a little hard to see right now, but that's what's happening. So when I say here, after increasing CP row high, let me remove this thing. I say load A with 4, which is a screen code for D. I'm still saving that, storing that into CP row low, comma Y. But now I've increased what was in high byte. So you see, we don't specify high byte in here, just specifying the low byte. But because the way things are set up, that's just how it works. So when you're constructing using this kind of method with the parentheses, you're only specifying the address of the low byte in here. So I could have written the address for the low byte, that's 20 here. So I could have written 0020 in here. Or what a lot of people like to do when they're working with zero page, just do this. This is address 20. So I could have done this as well. The important part is when using this method, we need to specify the low byte in here. But I like to use these labels. So I'm going to use that label in there instead. And of course, comma Y, this offset with Y. So where did my D end up actually? My D ended up all the way down here. So because let's see if we can keep track of what we did here. So the first one was these two, then we went 255, that's this one. And then we said increase high byte, and Y is still 255, right? Yeah, I'm sorry, I'm confusing myself now. The point, hopefully you see the point here. That by using this method, remember, this only works with zero page. By using this method of storing the low byte first and the high byte right after that. By doing that, we can construct an address, and we need to use the Y register. So we can construct any address we want, really. That's the main point here. And that's something that we're going to be using a lot. We need to make our own, or specify our own memory addresses in code. So low byte, high byte, storing those the right way in memory and combining them by specifying the low byte, the address, memory address for the low byte, specifying that in parentheses. So memory address for the low byte in parentheses, comma y, and the y becomes an offset. So 0, that's just this memory address, 1 is 1 address up. Okay, well, this like I said, it can be confusing, and I'm sorry, this is something that's super hard to explain. Hopefully you got what I was trying to say here, but this is something that's it's a little unusual, and this little endian thing is not helping with understanding this stuff. But as I said, this is how it works, so we just have to deal with it. But I do actually very much encourage you to play around with this, and hopefully you see how this works, because this, as I said, is something that we are going to be using a lot in our code. It's going to be super helpful for us. Alright, so just to wrap things up today, in just a few episodes we're going to see something that I like to call screen tables. So with using the method that we just saw, that 0-page technique, using that and some tables, we can place our character exactly where we want on the screen, with the right color as well. So hopefully, if you didn't quite understand the point of this 0-page thing right now, then hopefully you will get the point then. But this has been a pretty long, complicated episode, so as I said, hopefully you got this, and I'll see you next time. Bye bye.